pregunten más, ya en confianza.
¿Y tú cuánto tiempo tienes aquí en astronomía?
Desde el 2016.
2016.
Ajá, 2 años más o menos.
Ajá. ¿Dónde hiciste tus estudios? ¿Aquí
Hice
también?
aquí el doctorado.
Ajá.
Me fui de postdoc a Shanghai por un año.
Ah, Shanghai, no me digas, ¿sí?
Sí, sí, sí. Y estuve 2 en Santa Cruz, en California.
Ajá.
Ajá.
Santa Cruz.
En Santa Cruz, ajá.
Ajá.
Y ya después para acá.
Ajá.
Otra vez.
¿Y cómo te fue en Shanghai? Es interesante, hay que dar una plática de eso, ¿no?
Sí, 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 fue una experiencia muy interesante.
Sí, yo me sorprendí, yo estaba ahí en 2005,
Ajá.
en un congreso ahí,
Ajá.
y estaba fascinado con el desarrollo que
Sí, 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 la
tan
verdad.
fuerte, ¿no?
Ajá.
¿Subiste el tren de bala del aeropuerto a Shanghai?
No,
¿No?
sí ocupé los trenes rápidos, pero nunca el tren bala.
La magnetic levitation,
ajá.
¿no?
No.
Ajá.
Sí, fue una experiencia interesante.
Ajá. ¿Y cuánto tiempo estabas en postdoc ahí?
Un año.
Un año.
Un
Ok.
año, solo un año. Sí, ya después me fui.
¿Y aprendiste algo chino?
No.
¿No?
No.
Complicado.
Era complicado.
Todos hablaban inglés ahí en
Pues sí, bueno, sí, en el grupo en donde yo estaba todos hablaban inglés,
Ajá.
pero creo que a los chinos les daba miedo hablar conmigo en inglés.
¿No
Eran
fue,
muy tímidos.
¿No fue un chino que te invitó entonces?
Sí, yo estaba
¿Sí?
trabajando
Ajá.
con un investigador chino.
Ajá.
Sí, había como
Okay.
un poco de aislamiento.
Ok, ¿y los estudiantes?
Los estudiantes bien. Sí.
Ajá. ¿En inglés?
En inglés, pero les daba mucho miedo hablar conmigo en inglés.
Ajá.
Entonces muchas veces no hablaban, aunque yo los incitaba.
Hola, Vladimir, ¿cómo estás? Muchas gracias, sí.
Gracias.
Sí, bueno,
que
gracias.
Acá.
Sí, a ver si les gusta, no me corren ahí astrónomos, entre astrónomos es complicado, ¿no?
José, internos varios todavía.
Vamos a esperar.
Estamos con esto de contrataciones de plazas y están ahí en eso seguro.
¿Clases?
Son como unos 7, 8, con el director y con un par de...
Sí.
Y es día feriado, ¿no? Por las mujeres, ¿no?
Parece que
¿O no es
también.
oficialmente o no?
También está eso, ¿no?
Ajá.
Vamos a esperar un par de minutos.
Sí, ¿no? Tú mandas mails también, ICN, creo.
Ajá, le mando a los del ICN para que vengan.
Creo que no hay problema.
Yo creo que vamos a comenzar el coloquio del día de hoy. Hoy es un placer tener a Karo. ¿Cómo lo pronuncias?
Michaelian o
Michaelian.
Michaelian, aquí sí.
Okay. A Karo Michaelian del Instituto de Física. Karo hizo su licenciatura y doctorado en Alberta, Canadá. Después de ahí se fue a hacer un postdoctorado en Suiza y desde el 91 es miembro del Instituto de Física. Y bueno, el día de hoy nos va a presentar la plática titulada Spectral Constraints on Life Given Stars. Así que la va a dar en inglés, así que adelante.
Muchas gracias. Y muchas gracias, Vladimir, por la invitación. Voy a hablar en inglés, espero que no hay problema, es que seguramente me vas a entender mucho mejor en inglés que español. Pero si tiene preguntas o dudas en español está bien. Okay, so there are many or a number of different types of stars in the universe, and these are the most common stars in our galaxy. By far the most common are the M-type stars, and this is their population, 76% in our galaxy. And our G-type stars, only 7.6%. So an interesting question is which of these types of stars could harbor life? And when I talk about life here, I'm talking about life similar to our own. That is based on carbon and covalent interactions and in a water solvent environment. And probably utilizing molecules like RNA and DNA, very similar to RNA and DNA. Of course, one could imagine life completely distinct based on other elements, for example, silicon, and perhaps based on other solvents in exchange for water. But those would be too hard to predict. It would be too much of a guess to present anything with respect to life of these other kinds. So this question, which stars could harbor life, are now pretty relevant because, well, you all know that next year they're going to send up into space the James Webb Telescope. And this telescope will have some of its resources dedicated to looking for biosignatures on stars. So to have an idea which kinds or which classes of stars could possibly harbor life would aid a lot in being careful with resources. Oops. Something happened. Sorry. Okay. So this question has been studied before, and these are some of the people who have worked on this, which stars could harbor life. But these are basically works which are based on a traditional perspective, and they define a habitability, which is basically deciding which conditions are necessary for the production of organics, whether they be chemical or photochemical. And well, they usually consider low particle or ultraviolet destruction or mutation rates of organics. For example, the cyclobutane pyrimidine dimers, which are the major photoproduct of ultraviolet light on DNA and RNA. So these consider the ultraviolet light in general, not all of them, but in general, dangerous to the production of life or detrimental to the production of life. So the criteria basically in this traditional approach are liquid water, because it's a good solvent and it has many other properties like hydrogen bonding, which are useful for chemical interactions. And the planet has a magnetic shield to shield the atmosphere from charged particles, from erosion due to charged particles. And it has generally low ultraviolet radiation, but maybe some UVB or UVC if they're needed for photochemical reactions to produce these molecules. Okay, the perspective, well, these approaches are really what I would call ad hoc with respect to ultraviolet radiation. Okay, because there's no model based on the origin of life for these approaches. No? Essentially what they're trying to do is just determine which are the best conditions to produce these organics through chemical or photochemical means. Now the perspective I'm going to be introducing here is the thermodynamic dissipation theory of the origin of life. And instead of habitability, I'll talk about thermodynamic viability. That is that we consider life as a non-equilibrium thermodynamic dissipative structuring. So we consider the photochemical processes necessary not only for production, but also for proliferation and genome-level molecular evolution under dissipation. And the dissipation will be in the ultraviolet and the UVC. I'll try to convince you of that in a minute. So the criteria in this perspective is a little bit different. We require liquid water, a magnetic shield, and something new is continuous UVC and UVB radiation. And the UVC radiation I'll divide into actually 3 different parts. Short wavelength UVC, which is required in the upper atmosphere for dissipative structuring of some of the molecules, and long UVC radiation on the surface, which is also required for dissipative structuring, and medium UVC, which we do not require on the surface. In fact, it would be detrimental on the surface because this radiation could cause ionization of these molecules, which are produced on the surface by this long UVC radiation. And the ionization essentially causes the destruction of these molecules. But we also require another component, which is high surface temperature with diurnal cycling and a gradual cooling of the Earth's surface or the planet's surface through time. So before getting into that perspective, the thermodynamic dissipation theory on the origin of life, first present some of the physical conditions which were probably around at the time at the beginning of life, 3.85 thousand million years ago. These physical conditions are necessary because there wasn't any complex polymers or organic molecules, enzymes, to aid in the chemical reactions. At that time, there couldn't have existed these complex enzymes that exist today. So therefore, life and the proliferation and its evolution would have been more dependent on the physical conditions of the environment at that time. So it was suggested that there was a lot of volcanoes which were spewing out hydrogen sulfide, water, and carbon dioxide, and that the seas were hot, about 85 degrees centigrade. And they know that from the isotope ratios of oxygen isotope, oxygen 16 to oxygen 18. And there was probably a lot of asteroids and comets which were bringing in organic material, perhaps, although I don't require that in this analysis, but there could have been organic material being brought in by comets or asteroids. And the atmosphere, well, it's thought that it wasn't as reducing as Miller thought in the 1960s, when he did the experiments in the 50s and 60s. So the atmosphere probably contained a lot of nitrogen as it does today, a lot more carbon dioxide than today due to these volcanoes, and also water, maybe twice as the amount of water in the environment, some amount of methane, and probably some hydrogen. But there was no oxygen or no ozone, or very little, only due to abiotic interactions, for example, ultraviolet light destroying carbon dioxide and producing oxygen in the very upper atmosphere. But it was thought that there was very little, because it's very reactive oxygen. It would always, if there existed any at that time, it would have formed oxidation components with almost anything. So then if there was no oxygen or ozone, the UV light must have been very intense, particularly in the UVC. So I'll show you what the solar spectrum would have looked like at the beginning of life on Earth 3.85 thousand million years ago. So this black curve, this is a calculation. It's not a simulation, it's a calculation. This black curve is the curve that we calculate, given the different components and the best estimates for the concentrations in the atmosphere at that time. And the standard solar model, which is that the sun, for example, has gone through a period of increasing its radius about 11%, and the surface temperature has increased only about 1.5%. But overall, that gives an approximate increase about 30%, decrease, sorry, or now 30% increase over what the integrated output would have been at the beginning of life, 3.85 thousand million years ago. So there's a component here in the UVC, and these components here are missing because of the absorption by aldehydes, which are the most common or most stable molecules which are formed by UV light on these components in the atmosphere. Okay, for example, formaldehyde. And there was no oxygen, so therefore no ozone, this component could come in. And then we had absorption of hydrogen sulfide at this point, and carbon dioxide basically absorbed everything at lower wavelengths. So this is an expansion of this area here. This is at 3.85 thousand million years ago. And so we have an integrated flux in the UVC, which are called, this is I would call the long wavelength UVC, at about 5.5 watts per meter squared integrated at the equator and with the sun directly overhead. Okay, that's about 1% of the total integration of the flux, the energy flux. Uh-huh.
The most abundant molecule is
No,
nitrogen too?
Well,
or-
I didn't really think about it, but
No?
it seems to be. Yeah, nitrogen would be the most common, then carbon dioxide, then probably water. Yeah, yeah, looks like it is. I'm not sure, but I think it is. So we have this 5.5 watts per meter squared coming in. And this is not something I calculated, being calculated before. In fact, Carl Sagan, calculated it in the 70s. And he was the first to realize that this component would have been coming into the Earth's surface at that time. And at that time, it was thought that ultraviolet radiation was dangerous to life, and that life, therefore, had to be protected somehow. And that's why all these origin of life at the hydrothermal vents at the bottom of the oceans came about. Okay, and Carl Sagan, in fact, looked for different mechanisms which could have protected life, early life, from this UVC radiation. So Nossen et al., in fact, did a simulation. Now he's plotting here the ratio of the UVC light, okay, in more or less the same range that I showed before, compared with the UVC light coming in today at Earth's surface. Okay, and we find that, for example, in the Archean, when light began, there was about 10 to the 30 times more ultraviolet light at 260 nanometers than there is today. And that's not so surprising, because today almost nothing gets in to the Earth's surface in the UVC range. So that's why these. Yeah, this is ozone, which is ozone. In fact, if you look, okay, let me just explain. This is the DNA absorption. This is DNA absorption. Ozone, in fact, looks very similar to DNA absorption. So it cuts exactly at 260. It's where the peak in the absorption of ozone is today. It's also interesting that ozone is also a life-produced molecule, no?
Mm-hmm.
It's produced by life, just like DNA. So this is the absorption spectrum of DNA, and it almost corresponds directly, no, with the amount of light which was coming in at that time, the peak in the.
But today there is no DNA in the atmosphere to absorb it.
No.
I mean, what is now absorbing this radiation?
Now it's ozone in
Ozone?
the upper atmosphere.
Only ozone.
Ozone and a little bit of oxygen. Oxygen is a little bit lower. It's like starting about 210 or something like that.
Okay, thank you.
So not only does DNA absorb very strongly in this UVC range, in this long wavelength UVC range, but it also dissipates very rapidly. So this is the spectrum of the excited state, how it decays in time. So what they do, this is a pump probe experiment. So they have a pump which is a femtosecond laser pulse at 260 nanometers, and they pump the DNA or these bases, and then they watch how the excited state decays by using a probe, which is another laser at a different wavelength, a longer wavelength, and because they can excite it from the first excited state, they can excite it to the second excited state, and so they can measure the population of the excited state as a function of time for these bases. These are bases of DNA and RNA. And now the interesting fact here is that these dissipate extremely rapidly, on the order of picoseconds, 10 to the minus 12 seconds. They have two components, one very fast, which is sub-picosecond, and another one which is a longer time component, which is due to intermediate states in the bases. But basically, everything goes down to zero in less than 10 picoseconds. And how does it do that? It's because these molecules have what they call a conical intersection. And that I can explain simply. Just that when the molecule is excited by a photon, it goes to the excited state. And the coordinates of the excited state of the atoms, the coordinates of the atoms, can be slightly deformed. And that would mean that the vibrational states on the excited state can connect with the vibrational states on the ground state. And so the energy can go very rapidly. This electronic excitation energy can go very rapidly to the ground state through this conical intersection, okay, on the order of picoseconds.
Sorry, what are the axes?
Oh, these are just coordinates, and they are arbitrary coordinates. Okay, this is just a schematic diagram, but it would be,
Then that's an arbitrary diagram.
yes, it's an arbitrary schematic diagram, to try to illustrate the principle. The coordinates depend on the positions of the atoms, of course. These are the coordinate positions of the atoms, and it's much more.
I want to understand physically what is what you are showing.
Well, you have to read this.
Okay.
No, I'm not a real expert on this, but there are many articles that are written about this.
You're showing it.
Yeah, I'm showing it. This is just a schematic diagram. If I did it in 10 dimensions, you wouldn't make sense, heads or tails out of it, no? But I think you can get the idea that in the excited state, the coordinates of the atoms are deformed, such that the vibrational states on that deformed coordinate configuration match with the vibrational states of the ground state.
Oh, is the shape of the molecule?
Yeah, it's the shape of the molecule, the coordinates. Okay, so RNA and DNA then are very, bases are extremely rapid dissipators. And that also makes them then resistant to destruction by ultraviolet light. Okay, because there's no time for chemical reactions. Chemical reactions on the order of, well, hundreds of picoseconds. And this is the case in sub-picosecond time. So there's not even time for chemical reactions to occur in the excited state. So they're very resistant. And in fact, all of this work on this conical intersection is due to people thinking that, well, this is a mechanism to protect the DNA from this ultraviolet light which was existing at the time of the origin of life. But what I'm trying to say is something a little bit different. But I'll get into that. But just mention that the non-natural tautomers, you can change the position of the hydrogen, the protons. You can move them around the atom, and that produces a new tautomer. And these tautomers are also stable. And some of them are more stable than the natural bases, in fact. Okay? But these tautomers have much longer decay times, 2 orders of magnitude greater decay time than the natural tautomers. Okay? So therefore, we can say that RNA and DNA are excellent microscopic dissipative structures in the UVC. For example, 1 photon in the UVC gets absorbed on a base or 2 bases, and it dissipates. It converts into infrared radiation, 30 or 40 photons of infrared radiation in the order of picoseconds. So when it goes back to the ground state, so it's ready to receive another photon. So that's really the same thing which is happening here, with a hurricane. A hurricane is dissipating the temperature difference between the hot ocean surface and the cold upper atmosphere. And this is a dissipative structure. This is dissipative structuring. We know that, in non-equilibrium thermodynamics. So what I'm saying is that this also, DNA is also dissipative structuring. Okay, so it's like it's just like a small hurricane or tornado, and its only function at that time would have been to dissipate these photons of ultraviolet wavelength into infrared wavelength. That's the thermodynamic imperative. So I'll describe a little bit more about dissipative structuring. So I gave this example of the hurricane, but we also know that there are Bernard cells, and there are this Belousov-Zhabotinsky chemical oscillating reaction system. Okay, and this is spontaneous symmetry breaking in both space and time. Okay. And well, this is macroscopic dissipative structuring. So these structures spontaneously, I say spontaneously, but really they need a gradient, they need a force, a generalized thermodynamic force of the system to arise and to proliferate and to evolve. But I say that they are spontaneous. So I want to say that the same thing's happening, or did happen, with these molecules, DNA and RNA. For example, Ferris and Orgel found that 4 molecules of hydrogen cyanide in water under ultraviolet light of 260 nanometers, just where the peak was coming into the Earth's surface, can transform these 4 molecules of hydrogen cyanide into adenine. So it goes through various steps in the process, but it absorbs like 3 photons in the ultraviolet in order to get from here to here. And these are at different stages are also absorbing and dissipating. Not all of the photons that absorb produce the isomerization which is necessary, or the tautomerization which is necessary to go from one step to the other. For example, here, this is what they call cis-DAM. We see that if you look at the following one, trans-DAM, after the absorption of a photon, you have a rotation about the double covalent bond. And that rotation about the double covalent bond is something very natural or very common in nature. For example, in our eyes, we have a molecule which is called rhodopsin, and it's due to the rotation, but in the visible, due to visible rotation of a molecule, which allows the detection of light in our eyes. So this is something quite common, but this is in the UVC range. Okay? And there are other tautomerizations which occur in the process, and I'll show you that in a minute. But what I want to say is that these reactions, from here to here, can go uphill in energy, in Gibbs free energy, or they can go down, or at the same time, they could go downhill in entropy. That is, the system becomes more organized, precisely because you're coupled to a dissipation of a photon. Okay, so the entropy and the negative, or the low entropy in the photon, can be used to push this reaction forward in this direction. And the interesting thing is that successive structures here are in fact optimized to dissipate photon potential. And I'll show you that in this slide. Oh, sorry. So this is a little bit more in detail of what's happening. This was first demonstrated experimentally in 1966 by Ferris and Orgel. But Boulanger in 2013, they did the time-dependent density functional theory for these reactions. Okay, so they found, and they mapped the lowest energy excited state energy surface for the reaction. And what they found is that for this reaction to go forward in this direction, you need absorption of at least 3 photons. All of those photons have to be greater than 4 electron volts. So it's in the UVC region around 260 nanometers. And well, the interesting thing is that if you look at the wavelengths of the isomerization, to go from one step to another, when we absorb a photon, they bounce around this area. This is the UVC, which was coming into the surface of Earth at the time of the origin of life. So it's bouncing around like 254 here, and then it goes to 325 here, and then 275, which is here, before it finally settles down to adenine, okay, which is absorbing at 260, just exactly where the peak is in the light which was coming in, and it has a very large molar extinction coefficient. So it's absorbing very strongly, exactly around 260. So I look at it kind of like a hurricane, which has been growing and evolving to dissipate ever more efficiently the ultraviolet light which was coming into the Earth at that time. Sorry. So you might ask, well, what about hydrogen cyanide? Because I didn't include it in one of the common gases in the atmosphere at the origin of life. But it's been shown also by Dodonova and Trainer that ultraviolet light of this radiation, 145 nanometers, okay, which I assign short wavelength UVC radiation. This on nitrogen and methane can produce hydrogen cyanide. And this radiation wouldn't have gotten to the surface because it would have been absorbed very quickly by carbon dioxide in the atmosphere. But it could have got to the upper atmosphere. And so this which I want to show is also dissipative structuring of hydrogen cyanide using shorter wavelength radiation. Okay, so we can get hydrogen cyanide from shorter wavelength, from just the gases in the atmosphere and shorter wavelength radiation. Now there's also a route to ribose, which is the sugar known in DNA, through formaldehyde, which is one of the aldehydes, which is produced by ultraviolet light on the traditional or the most common gases given out by the volcanoes. You can get that through this what's called the Formos reaction, which is just water and formaldehyde and shorter wavelength radiation can produce ribose. So you can in fact produce these components. Now you also need something else in order to get the bases to, well, they will stack, if you just have the bases in water, they will stack one on top of the other if the temperature is not too great, just due to the stacking interaction, the pi interactions between the two bases. But to get them to form the chain, which is the single-strand DNA, you need the bases to be activated, they call it, or phosphorylated. So we need 3 phosphates here, and breaking off 2 phosphates gives you enough energy to form the chain, the single-strand DNA. Now they've also shown that this phosphorylation of the bases can be performed by ultraviolet light in the long wavelength range of UVC, 260 nanometers, around 260 nanometers. Okay, so we have all the ingredients from ultraviolet light to produce DNA, single-strand DNA. Now, not only the bases of DNA and RNA absorb in the ultraviolet and the UVC range, but in fact, most of the fundamental molecules of life absorb in this range: the nucleobases, cofactors, amino acids, many amino acids, not all of them, but many of them, and vitamins, proteins, which are based on some of these, these amino acids, these proteins which are in all the 3 domains of life. That's why they're called fundamental molecules, because they're in the archaic, in bacteria, in the eukaryote. Okay, so these proteins are based on some of these amino acids, and they're common to all 3 domains of life. That's why they're included in the table. And also some pigments and even lipids absorb in the UVC range. So they're all absorbing around here. And in fact, if I plot the maximum absorption or the peak in the absorption, in some cases there are 2 peaks on this plot, then you will see something like this. So you get, so these molecules are all absorbing around this peak, which was predicted to be coming into the to the Earth's surface at the origin of life. So probably, and that's what we're looking at now with some students, is that many of these molecules, these fundamental molecules, might be in fact dissipative structuring, just like I showed for the case of adenine in the ultraviolet. Okay, but what about the proliferation? That's the production of these molecules. But proliferation is something else. But also from non-equilibrium thermodynamics, we can explain proliferation. And Prigogine first showed this, for example, with an autocatalytic chemical reaction. So let's say that we take a reaction and we have A, which is the reactant which is coming in from the environment into the system, producing an intermediate X, and then the final product B, which is sent out to the environment. So A and B are fixed. They are like the chemical potential fixed over the system from the environment. And let's also assume that we have an intermediate product X, which can go to another product M. But this M is rather special because it acts as a catalyst for this reaction A going to B. For example, in this case, it could be A going to X or X going to B. If it acts as a catalyst, then we can show with non-equilibrium thermodynamics that the concentration of M will increase in the system with respect to what you would expect if it was a system in equilibrium. No? And the factors can be many orders of magnitude greater. No? And not only that, well, it's rather obvious that the global entropy production of this system will increase as M increases, okay? Or if M is a good catalyst, then the entropy production of this chemical reaction will increase. So now we can do exactly the same, but considering autocatalytic photochemical reactions or dissipation. Here, for example, this is also schematic. We take a solar photon spectrum, at this temperature, the surface temperature of the sun, and the Earth photon spectrum, temperature of Earth's surface. And we have an intermediate. Let's say this is some intermediate on the way to adenine, for example, that I showed in the previous slides. And this has a photon spectrum of about 2000 K. If you absorb one photon, the temperature of the molecule will go up to about 2000 K. And let's say that this finally produces another product, M, which acts as a catalyst for this dissipation. Then, by the same reasoning or the analogy with the completely chemical reaction, we could expect the concentration of M to increase over and above what you would expect in equilibrium. And you would expect the dissipation or the production of entropy to increase for the system. That seems to be the tendency of nature to, and also if you look at the biosphere, there's been a tendency of increasing the dissipation as a function of time in the biosphere. So it's like a natural imperative, even though it has not been shown theoretically that there is this natural imperative to increase entropy production. We have a lot of evidence, experimental evidence, for that occurring in the biosphere. Okay, so now I'll give you an example of one of these autocatalytic photochemical reactions, which is what I call enzymeless replication of RNA and DNA. Now remember, I told you the temperatures of the ocean surface were hot, about 85 degrees centigrade at the origin of life. And this temperature is very interesting because this temperature was determined completely independently of anything that had to do with DNA, right? It had to do with the oxygen isotopes. But this temperature is very, very close to the denaturing temperature of DNA. Of short strand or intermediate strand DNA is about 85 degrees centigrade. Okay, so we imagine that the Earth's surface was slowly cooling, and at the origin of life, or just before the origin of life, it was hotter than 85 degrees centigrade. So we would have single-strand DNA and RNA floating on the ocean surface, dissipating the ultraviolet light which was coming in, and that was its thermodynamic function. But now as the ocean surface temperature cooled, then two strands could come together, if they were coupled, if they were analogs, one of the other, and form a double-strand DNA. Now, if the temperature cooled sufficiently, this could never denature again. So it would be stuck in a double strand and you wouldn't get any replication, because to have replication, you first need denaturing. But you can imagine that at that time, there was this ultraviolet light coming in. So in the daytime, or in the afternoon, when the surface temperature of the ocean surface was hottest, due to absorption of infrared light and also absorption of these UVC photons in DNA and RNA. And you can imagine that this would denature into two separate single strands. Okay? And then at night, when the surface cooled off and there was no UVC light coming in, you would get, again, renaturing, or the production of two double strands where you had one single strand. Yeah, question?
Well, if that was the temperature and there was an ocean, would you not expect the Earth to be covered by clouds?
No. For example, at hot temperatures, you get more. It was estimated that there's about twice as much water vapor in the atmosphere at the origin of life as there was now. Okay, more or less. That's an estimate. I don't recall exactly how they came up with that estimate, but it was about twice as much. So there certainly must have been some clouds, but also the fact that you have a hotter atmosphere implies that you can carry a lot more water without condensing or forming clouds at that time. So it's not obvious that it was completely clouded. So this is template directed. This is autocatalytic because these templates act as a template to produce a second strand of DNA. That's why it's autocatalytic, this interaction. And it's also tied to dissipation because you need the photons, the UVC photons, to denature DNA. Okay, so we have replication tied to dissipation. So those DNAs, which were suchly configured that they could denature most easily under ultraviolet light, would be those that denatured and so could be replicated in the second diurnal cycle, in the next day. So this is what this replication tied to photon dissipation. And that's really the idea that is important here, is that we're tying something, life or the evolution or the production of these molecules and their proliferation, to dissipation, photon dissipation. Life is an irreversible thermodynamic process, so it has to dissipate a photon potential or some kind of generalized chemical potential. In this case, we're talking about the photon potential, the UVC potential.
Sorry for interrupt you, but but these conditions you can more or less simulate in a laboratory, no?
Yeah. Mm-hmm.
And no one has tried to do that?
Yes, I can maybe go to. So you might think it's you might think it's all hypothetical, right? But
it was not prepared, eh? It was not.
it was good timing, your question. So we did the experiment, no? Not quite like simulating the real Earth environment at that time. So we had here, we had a temperature-controlled unit where we had in a quartz cuvette the DNA in buffer solution at pH 7. And we had an ultraviolet light, which is a deuterium light, which has a continuous spectrum from about 200 to about 500 nanometers, so into the visible also. And we had a spectrometer that measured the absorption of DNA. And we had another spectrometer which measures the dispersion, even though we finally didn't use this data because we couldn't make much sense out of it. But we also got dispersion from this absorption data. So this is what the raw spectra looked like. This is the absorption of DNA at 260 nanometers is where the peak is. Okay, and this is a function of temperature. This is the scattering region. This is an amplification of this region, the scattering region. So you can see that as we increase the temperature, we start to get denaturing at about 65 degrees centigrade. And this is synthetic 48 base pair DNA, which was made here in the Instituto of Fisiología Celular. And we also had natural DNA. And we see this effect, same effect as we increase in temperature. We get a denaturing, which is seen by this, what's called hypochromism. When DNA denatures, then the bases are less stacked. They become more free to wander around the axis of the DNA. And so it opens up like an umbrella. And so the absorption increases. So you get an increase in absorption with denaturing. So this is double-strand DNA, and this is single-strand DNA. And you get an increase about 30 or 40% on the complete denaturing of DNA, or RNA, the same. So this is what we're seeing here. This denaturing is a function of temperature. Okay, now we wanted to see if we got denaturing as a function of UVC light. Shining UVC light would it denature double-strand DNA? So what we did, for example, this is with the salmon sperm DNA. We raised the temperature to about 40 degrees centigrade, below its denaturing, natural denaturing temperature. And then we let the system relax for some time period to come to some kind of an equilibrium. And then we turned off the UVC light and turned it on, turned it off and turned it on. And we measured the extinction, which is really the absorption. This is the absorption peak. We measured this peak here, which I call extinction because part of it is absorption, but another very small part is due to dispersion, the scattering of light by DNA. And so this is interesting because every time we turned off the light and we left the system for about half an hour, this is a function of time, the absorption will go down. So it's like renaturing again, going back into its double-stranded form from single strand. And every time we turn on the light, it would start to denature again, separate. And this is very sensitive. This is a small amount, but we could measure it with our system that we had. it turns out, for example, for 25 base pair DNA, we get about 25% denaturing per hour under the intensity of the UV light that we had in our experiment. And our experiment was about 1/20th the intensity of the light at Earth's surface in the Archean. And we did that for all the other DNA samples, and we found every time we turn the light on, we get an increase in the absorption or the extinction. And every time we turn the light off, we get a decrease, and the same for 25 base pair DNA, synthetic DNA. So what is the mechanism for this? And first we thought it was due to a thermodynamic process in which the energy in that photon, which is 4.8 electron volts, would be distributed over a given volume. So the photon would come in, would absorb on one or two bases, and the energy would be dispersed over a given volume in a certain time period. And what we wanted to determine was the size of this volume, which would increase the temperature by about 3 degrees centigrade, which would be enough to cause denaturing of DNA at that temperature at 40 degrees for the salmon sperm in water without salt. Okay, and so we did the molecular dynamics, or really my student Adriana did the molecular dynamic simulations for this, and well, we had to really make some approximations because we didn't have time dependent density functional theory. We had amber potential model, and we had no excited states, so we had nothing to do with quantum mechanics. It was all a classical mechanic situation. And it turns out that it doesn't really affect the DNA, so this probably, we didn't see any separation or anything part of the normal. So it may have been because amber was not a good model for DNA, and we're still working on that. But we're now beginning to think that really the effects are really quantum. And for example, this is called light-induced proton transfer. This actually exists. You know? So you shine light, this UVC light, on bases, and if they're paired, then we can get a hydrogen going from one base to another. Let me just see. For example, this hydrogen here, after absorbing a photon, can go to this nitrogen from this nitrogen. So there's like a jump. So we get hydrogen bonding here instead of here. And that's one proton transfer. And that changes the charge distribution on the bases. And once the charge distribution is changed, also the pi stacking interaction will change, will be debilitated. So this is actually an uphill. So these are higher in energy than this. So that reduces the denaturing temperature, if you like, of the DNA. And not only one proton transfer, but you can also get two proton transfer. In this case, the two protons. This proton has been transferred to the oxygen, and this proton has been transferred to the nitrogen here. So you can get two proton transfer. And these are more or less stable. They can exist for hundreds of nanoseconds, which would be sufficient time to allow denaturing. No, if we get a number of photons which were causing the base stacking to deteriorate from one to the other, then after a certain period of time, we would expect we get denaturing maybe, and that's what we're thinking is probably what's occurring. We also have some mechanical effects. For example, once some of these end hydrogen bondings of these two base pairs are destroyed here or here, then it's more likely that the system will denature. Okay? So there are a number of effects, and that's what we're studying now with Adriana to find out what's exactly going on. So the future then, so I showed you up to here. So this seems at least plausible, no, that we could get denaturing at high temperatures, ocean temperature. That's why we call it ultraviolet and temperature-assisted replication. But now we have to show that there's a possibility of extension. 10 minutes, okay. There's a possibility of extension. And this, well, has been showed already in other experiments, or other people have done this. So there's no problem with extension, really, as long as we have magnesium, a double charged ion, then as a catalyst, then we can get extension at lower temperatures. So we think we have a system, no, for the DNA replication using environmental conditions and without enzymes. And we can also talk about the homochirality. Homochirality is important because if we have a system of mixed homochirality, then we don't get extension. Extension is frustrated by having mixed chiralities. So if you have right and left-handed DNA together in a single strand, it's not going to replicate. But homochirality then has been an important question in the origin of life. How did it arise? Well, just rapidly, I will say that if you have sunlight, which is coming into the ocean surface and it's being dispersed of a water molecule or of any compound in the molecule, then it becomes linearly polarized after its dispersion, after its scattering. And then if there's a total internal reflection at the surface, you can get circularly polarized light. And the direction of circular polarization depends on the direction you're looking at the system, or it also depends on whether it's in the morning or in the afternoon, the sun. Whether it's on this side or on that side, that changes the circular polarization. But there's an asymmetry in the system because in the afternoon, the ocean surface temperature is warmer. So it would be more likely to denature in the afternoon than in the morning. So, and also DNA, I have to show, is that it has circular dichroism. That means it absorbs slightly more right-handed circularly polarized light than left-handed circularly polarized light. Okay? So that after a number of, I won't go through all this, but this is just a very simple recursion relation, taking into account these, the amount of right-handed circularly polarized light excess in the afternoon compared to left-handed circularly polarized, and the amount of circular dichroism of DNA, which is like 0.07%. And plugging it into this recursion relation, we can show that the homochirality in about 80,000 years would come up to 100% homochirality. 80,000 years is nothing, no, in the origin of life. And now if we include an energy threshold, and it's saying that only if we absorb a certain number of photons or a certain amount of energy in the system will it denature, then we can even reduce this time even further to about 800 years, okay, including energy threshold. I won't go into the details, but I have an article if anybody's interested in this. Here you can find the articles. So what about evolution then? Well, so far I have described everything as being photon dissipation. So anything in evolution, anything that occurs in evolution would have to increase the photon dissipation in order to be thermodynamically plausible, no? To have a thermodynamic imperative for evolution to occur. So I'll just give you one example. No, this is tryptophan, for example. This is a fundamental molecule in all of the domains of, in the 3 domains of life. And it also absorbs very strongly in the UVC, but it doesn't have a conical intersection. So it doesn't dissipate very rapidly. It takes nanoseconds, the order of nanoseconds. And it also has a fluorescent component, which means it's not very dissipated because it's giving out another photon, which still has to be dissipated later on. But if tryptophan is close to DNA, within a certain number of angstroms, or 1 or 2 angstroms, then it can pass its electronic excitation energy onto DNA, onto the bases, and use the base conical intersection to dissipate that electronic excitation energy. So it's called resonant energy transfer. And this is already known, and they use it, in fact, in measuring interactions between different molecules in the laboratory. So tryptophan, and the interesting thing is that tryptophan has chemical affinity to DNA, and not only DNA, but to its codon. Okay? So this is a way of getting information through dissipation. Increasing dissipation. Information is stored. No, information stored is in the codon, which is the chemical affinity to tryptophan. That's the information stored in the codon. So the system acts as a greater dissipating system. So we get information related to dissipation and the dissipation evolution relation, because this is really evolution, the system becoming more and more complex in such a manner that the sum is greater, the 2 parts together are greater than the sums, the individual sums of the 2 parts. Okay? Tryptophan using the conical intersection of DNA to dissipate. Okay, so very quickly now, because I don't have much time, these are all the UVC dissipated processes that I have talked about. This is just a summary. We need this ribose and the production of hydrogen cyanide in the upper atmosphere with the short wavelength radiation. We need also long wavelength radiation to produce the bases, phosphorylation, and we need this ultraviolet temperature-assisted replication mechanism, which doesn't use enzymes. We have proliferation through this autocatalytic photochemical interaction. We have homochirality and evolution. And we have one thing which I haven't talked about, which is really detrimental or against this, which is the ionization of these molecules. If you ionize them, you lose electrons, and then they become other molecules, or they they don't bind anymore as they should. And so now I'll get to the reason that I am here. This is the spectrum plotted of the different types of stars. This is the A star and the F star, and this is our sun, which is a G star, K star. This is AD Leo, which is an M-type star, but a very active M-type star. And this is the normal M-type star. So these are the spectrums which you would get of the photosphere. Okay, and in the case of AD Leo, it's very active, so it has a region in the ultraviolet, which I've also included in approximation calculation. So, and these are the regions. This is a long ultraviolet wavelength region, which is necessary for dissipative structuring, proliferation, evolution. And this part here is the medium ultraviolet, which is detrimental because it causes ionization of the molecules. And at the top of the atmosphere, this is at the planet's surface. So I'm taking a planet which is very similar to Earth, which has the same gases as the Earth. And this is the top of the atmosphere for these stars at the planet. Okay, and this is where the short wavelength UV radiation comes in. So each one of these stars has a different component. So the three components, the short, the medium, and the long wave UVC radiation, which are important to this process, if you believe this of the dissipative structuring of life. So we can integrate, for each of these stellar spectra, we can integrate the regions here. And these are what we get. So what we try to do is that all stars have the same integrated flux over the whole wavelength range of about 500, or about 500 watts per meter squared, which is what the Earth had at the time of the origin of life. Okay, so we adjust the distances of the stars, so they all have about 500 watts, and that's to get liquid water. We need about 500 watts in order to get liquid water. So we adjust the distances. These are the distances of the stars. The M-type star is a distance of 0.16 astronomical units, very close to the star itself. And the A star is 3.4 astronomical units. The planet would be at 3.4 astronomical units distance from the star in order to have liquid water on the surface. And then at these distances, we integrate the spectrums, and these are the numbers that we find. For example, the Earth had about 5.5 watts per meter squared of UVC in the long wavelength range. So remember, the long wavelength range was for dissipative structuring, phosphorylation, denaturing, proliferation, homochirality, and evolution. And the medium is detrimental. Here I plotted the ionization potential of the bases. This is for cytosina, this is thymina, as a function of energy. And so I plotted here, this is 160 nanometers, so we're just starting to get, these would be lower wavelengths here. We're just starting to get ionization at about 160 nanometers. So this light is really detrimental. Well, this light here would be detrimental. And we also need the short wavelength in the upper atmosphere to produce hydrogen cyanide and ribose. So we have these fluxes, of long ultraviolet wavelength radiation, medium, and short. And so now the question is, how could we form a probability for life if we assume that we need these wavelength ranges? Certain are detrimental, so they would come in as a negative exponent. Okay, so we need a way to pesarlo, so poner un peso on each of these. So we put a factor which is dependent on the number of independent dissipative structuring, proliferation, evolution processes. In the case of long wave radiation, this is very useful radiation and is needed in many steps. For example, in what I've showed, there's 6 steps. And this medium wavelength radiation is detrimental, We only need one step to ionize the molecule, and then it's destroyed. It's not useful anymore. And also for the dissipative structure, we don't actually really know what these numbers are, but there's some kind of a weight into how this this range of radiation would be useful for the dissipative structuring of life as I presented it here. So now we can form a probability of life occurring, some constant times all these factors, and these are the fluxes in watts per meter squared at the surface of the planet. And also maybe a factor for the age. The longer the age, the greater the probability you would have of life occurring. So this is the maximum age. For example, these stars, well, M-type stars last for many thousands of billions of years, but we don't have thousands of billions of years in the universe. We have only like 15 billion years, and our galaxy has only 10 billion. So the maximum age for these M-type stars, I put at 10 billion. K-stars also 10 billion. Our sun has 5 billion. F-stars 3 billion. A-stars 370 million years. So including all these factors, and then normalizing it to give a probability of life occurring of 1 for the sun. These are the factors for the other stars, according to this relation. Okay, so for example, the K-type star would be 100,000 times less likely of life to be produced. Okay, and that's essentially because, that's essentially because it doesn't have, that's essentially because it doesn't have any ultraviolet light radiation on the surface of the planet for these K-type stars. And AD Leo, which is a very active M-type star, is about 1 million times less probable. Okay, and these normal M stars without activity, well onto the main sequence, would have a probability of 10 to the minus 18, the probability of life, if you believe this relation with the wavelengths. And these other stars, F star would have 10 to the 3, and the A star 7 times 10 to the 3 times probability. So for example, here we would get only bacteria because we had only 370 million years. So there should have been life on these stars if this was the way life was produced. But we would only probably get the bacteria because we have only 370 million years and the star destroys itself. And well, F stars, we would get about 3 billion years, so we would get the plants and maybe sea animals, but not intelligence, no, because we've taken like 5 billion years to get to here where we are now. And these would probably only have these fundamental molecules like hydrogen cyanide, primordial molecules, and ribose, but nothing else. And these M stars probably wouldn't have anything. So the conclusions then is that we need like 3 components of ultraviolet light in this application to determine the probability of life. One is for dissipative structuring of hydrogen cyanide and ribose in the upper atmosphere, and that's in this wavelength region. The other one is a medium wavelength on the surface. This is detrimental. We would ionize. And we also have a long wavelength, which is necessary for dissipative structuring the fundamental molecules, denaturing, proliferation, homochirality, and evolution. We need also high surface temperature and decreasing slowly, diurnal cycling to get this replication, UV-TAR replication process occurring. And so the only suitable stars for the origin of life as we know it would be G and F type stars. And these stars would not be suitable. So the only place we should really be looking, according to me, for biosignatures are on these G and F type stars. But these M stars, K and M stars, could possibly have life, but not originated on the surface. They could be like from panspermia, from a meteorite coming in and bringing life, when it was already sufficiently developed and was using visible light. So it could have, these M-type stars, or K stars, could have life. And finally, I just want to acknowledge all the students. There have been about 12 students. Some of them are here today. And a collaborator in Macedonia, which is Alex Simonov. And thank you very much. And I just wanted to say that I have a book also, which is available on ResearchGate. If you want to download it, it's free. Just look for my name here on ResearchGate, and you can get a beta version. It doesn't have much of the star stuff in it, but it has the origin, thermodynamic origin of life in that book. Thank you very much. And any questions, it would be a great pleasure to answer.
Okay, thank you very much. We have time for a couple of questions.
In your almost last slide, you showed probabilities that right there, larger than 1. What do they mean?
Well, it would be like this for the F-type star would be 1,000 times more likely that life arose, or 1,000 times quicker life would have arose with respect to the sun. So that's just normalizing this with this constant here for the sun equal to 1. And that's what this would give. This equation would give for this star.
Okay.
So it would be 1,000 times more likely. And in this case, 7,000 times more likely.
I'm not expert in this topic, but apparently you are the person on the planet Earth who has solved the origin of life. I've
Well, I
read
wouldn't
many
say that
papers
either, but
in which they say that is a very difficult problem how you get to DNA. And in fact, there are several possible theories. You go through RNA, you don't go through RNA. You are telling us that you already know how to do it.
Well,
This puzzles me. And you show us some generalizations about nonlinear thermodynamics, but you haven't shown the specific steps. And I know why, because it's very difficult.
No.
So
well, some of
aren't
them-
you generalizing from some very vague concepts all the way down, all the way up to life? I mean, it really puzzles me.
Yeah, well, there are some more details.
Well,
Of
that
course, in
book
this
is published by you.
Yeah, but it's much more here than what I was able to say today. Much more detail is here. You find a lot more evidence and a lot more detail.
But I
here.
wonder about the acceptance within the general community that really works on this, about your theories.
Generally, they don't accept it. And not because
In fact,
they
several of your
found
publications are in journals in which you are the editor.
Yeah, journals leave it on the historical process has been that the article comes to the desk of the editor, and it stays on the desk for about 2 years, and then it gets published. It takes about 2 years for publishing. We have students here who need their articles to graduate. So it takes a long time because they're
No,
not,
what
but
I
we
mean
get
is
them
that
published. We
this
have
is a
our-
very difficult
We have,
problem.
for example, now maybe
But
12
You're
articles published.
making very sweeping
Well, I had to.
statements.
I had to.
I'm puzzled about this.
Well, if you have a specific question, I can try and answer it for you. I'm not sure I
Well,
will
for
give
instance, you are saying that ultraviolet light,
Yeah.
rather than being detrimental, it helps us to structure
Yeah.
organic molecules.
Yeah.
Well, last time I did an experiment which was going to the beach and not put in a solar protector, I really had trouble.
Yeah.
So how is that you
Okay.
can use ultraviolet light to structure molecules?
Well, I'm talking about fundamental molecules, okay? There's, of course, a lot more. There's a lot more in this than just what I presented here. But what I wanted to show you, what I wanted to show you is that this ultraviolet light in the UVC, which now doesn't arrive on the surface of Earth because of ozone, was around for 1,000 billion years, okay?
Yes.
So what
you have a
everybody
big
will- so-
oxygenation of the atmosphere.
Yeah, before the oxygenation of the atmosphere at 2.7 giga years. Okay, so what is the most probable? That life would adapt to it after 1,000 billion years, or it would hide from it 1,000 billion
Well,
years?
the problem
no?
here is not whether life adapts or not. How originates? That's the problem.
Yeah, well, this is really the origin. Dissipative structuring, just like a tornado.
But this is
Or
hocus
hurricane.
pocus. I mean, all of these steps are based on theories or in experiments. And have they done the experiments to do all the different steps to go all the way to the
Well,
basis that form the DNA?
Well, of course, I've given you the experiment that we've done. That's the only experiment we've done, which shows that DNA can denature. Oh, we're beginning with this. No, we have like maybe 7 years in this now. So we don't have all of the details. And of course, to get to humans, that would be a completely another story. But the general idea that I want to give to the audience, the public, is that life arose through dissipation. That's what it's doing today. If you look at life, it's not doing photosynthesis. There was, in fact, if you just give me a little bit time here. I skipped this slide, but I shouldn't have. What I wanted to show you today, what is life doing? This is, for example, Lake Louise in Banff, Alberta. And you can see that the forest is almost black. It's absorbing almost 100%. It's absorbing from about 200 nanometers. This only starts at 300 nanometers, but you go down 200 nanometers, it's also absorbing. So it's absorbing all this light, about 90% efficiency, up to the red edge. Okay, and only 0.1% of that light, the free energy in that light, is being used in photosynthesis. So the rest is dissipation. It's just dissipating, it's just dumping it into heat. And then there are other processes, abiotic processes like the winds, ocean currents, and the water cycle, which are dissipating the rest, no? Once we get dissipation into heat, this heat goes into producing winds, ocean currents, water cycle. So that's what thermodynamics, that's what the biosphere is. It's just a big thermodynamic engine dissipating, evolving to dissipate ever more the photons which come in, starting at the UVC range and then going into the visible range. And it started at the UVC range because in that range there was enough energy to make and break covalent bonds, but not enough to ionize, which is in the medium wavelength range in UVC. Okay, so that's what life is doing today. So it's very reasonable, at least plausible, to assume that it was doing that at the very beginning also. And of course, this theory is we still have a lot of students, and they're all working on it, and there's a lot more to be done. Oscar, for example, now is looking at phospholipids, how phospholipids could be dissipatively structured also, because they're part of the cell membrane. If we want to go from molecules to the cell, for example, we need to talk about phospholipids. So there's a lot still to be done. This could go on for another decade or hundreds of years. But I mean, this is the start. This is an idea. And I haven't told you how it developed, and I haven't told you that I'm assuming that we've discovered the origin of life yet. No, just presenting this idea and looking for criticism and comments to help, no?
Okay, well, it's a bit late.
But let him know.
We can talk in the
okay.
after
Yeah.
parties. So let's thank again to Karo. And we have the snacks and the after parties to have a more informal chat.
Okay, thanks, Aldo. Sorry for passing over time. Can you take that out?
Thank you very much.